Welcome, TGIF Friday. I guess it would be TGIF.
Yeah.
Yeah, it is Good Friday, so but all Fridays are really pretty good. Just ready for the weekend. Today we want to continue on working on those enthalpy of fusion. Whenever you hear the word enthalpy, by the way, you know how you take a foreign language, a lot of y'all may have taken Spanish and you learn, como está usted, and you have to translate that to how are you, or tengo hambre, just hey, I'm hungry. And so, and important ones, donde está el baño? So, when you hear the word enthalpy, it's like a foreign language because it really is kind of Latin derived. And so that always just needs to translate to the word heat. Enthalpy and heat are going to be synonymous. So enthalpy of fusion, heat of fusion are going to be the same. Enthalpy of vaporization, heat of vaporization, that's the same thing. Okay, enthalpy is just a fancy word for it. Okay, now but yesterday, and just a quick review, yesterday we talked about pressure, okay, and how to measure pressure and about atmospheric pressure. So I have this little thing right here that if I do this, push it down and then do that, I can't get it off the table. Okay? Why not? Okay? We think about suction, okay, and we hear about, this is a suction cup. But there really isn't suction. What's keeping it on the table? The pressure of the atmosphere pushing down on this, but by pushing it down and pulling this thing up, it pushes all of the air out from underneath it. So there's nothing pushing up anymore. And so there's no unbalanced force. But right here, as soon as I lift this up, the air is pushing up, so all I have to do is overcome gravity. But here, there's no air underneath. We've removed all the air, so there's only the downward force of the atmosphere, 14.7 pounds per square inch. So if there's like 6 or 8 square inches on here, then you multiply that by 14.7. So then we're closing in on 100 pounds that I would have to be able to lift up, and just right here, I'm not strong enough to do that. Now, if I got on top of it and whatever, I'm sure, I can pull up. But all I do is I push that down, then that lets air in. That lets air in. And now I can pick it up. Okay? And so because the air is pushing up with the same force on the inside as it is outside. So the atmosphere is constantly pushing on us. Okay? And what do we measure? What are the units that we measure pressure in? PSI is one. What does PSI stand for?
Mercury.
Pounds per square inch. KPA is kilopascals. That's the metric one. Torr, which is a millimeter of mercury. Okay, and atmosphere. I heard several people say something. Atmospheres. Okay. All right. Then we also looked at a bunch of graphs yesterday, and so I encourage you just to kind of, as we're moving forward here, just to really, those graphs are super important to make sure we can understand how to interpret all those graphs. All right, the graph that we were working on at the end of the day yesterday looks like that. Where this is temperature in degrees Celsius, this is heat added in joules. Okay, and this is actually level. Closer to level. Okay, so on this graph, what state is the substance in here at this point? I'm going to label this point A, point B, point C, point D, point E, and point F. Okay? Now, From between A and B, what state is the substance in? That's a solid, okay? It could be ice if it's water, but for any substance, it's going to be a solid. Okay, what about C and D? That's when it's in the liquid. And then E to F is the gas. Okay? Now notice in all three of those, A to B, C to D, E to F, we have a change in temperature. The temperature is increasing. So we're going to use what equation to measure the amount of heat? Heat is Q. And Q is equal to MC delta T, MCAT. Because what type of energy, kinetic or potential, are we gaining or losing here? Okay, but what type of energy? Kinetic energy. Temperature is a measure of the average kinetic energy. How fast the molecules are moving. Okay, but what's happening between B and C? Melting. So if I'm going melting this way, we're going to be freezing this way. Okay? And what type of energy is being used or given off on this one?
Heat of fusion.
The heat of fusion, but what type of energy? Kinetic or potential is it? Potential energy. Remember, which is latent heat or hidden to the thermometer. A thermometer doesn't measure changes in potential, so we're still adding heat. The water has a greater potential energy than the ice does. Okay? Because we broke the bonds, they now have the potential to come back together again. Breaking bonds always requires energy. Forming bonds always releases energy. Okay? So anything we're going this way is going to be positive. We're putting energy in, requiring energy to do that. If we are coming back down this way from a gas all the way to a solid, all energy is going to be released. The same exact amount. Okay? That's what the whole idea of potential energy. You put energy in, it now has the potential to release that same amount of energy back. You're putting in the energy. Just like I lift a book up, I'm putting energy into the book to lift it up. It now has the potential to come back down kind of all on its own. Releasing the same amount of energy that I put in. Okay? That's potential energy, energy of position. All right, so what we want to do today is we want to calculate anywhere along this, how much energy does it take to cause a certain transition. So let's just say an example. Okay? How much energy is needed to boil 100 grams of water at 25 degrees Celsius is needed to boil 100 grams of water at 25 degrees Celsius. Okay, so we want to boil it completely. Okay, we just want to boil it. But where am I going to start on this chart? At 25 degrees, is the water going to boil? So 25 degrees is going to be somewhere like right here, right? So I've got to go from here to figure out how much energy it takes to get to there, which for water, what temperature is that going to be? 100. Okay? This is 0. So I have to figure out how much energy is it going to take to go to here, and then to boil it, I have to look at how much energy it's going to take to go here. And remember, this is where we're going to use Q is equal to the mass times your heat of vaporization, and then Q is going to equal the mass times your heat of fusion. And remember, all those numbers are always going to be given to you. So what do we think we need to do? What's QT? Let's just say what the total Q. What do I have to measure?
How much energy is using for 25?
Okay, so the Q of the water from 25 to 100, right? So it's going to be Q of water from 25 degrees to 100 degrees. Then what? To boil, have the energy needed to boil it to go from here to here. Okay? So we have Q boil. So we only have, now, once we get to there, that's all the question asks for, just to boil it. It doesn't say to take the steam up to any other temperature or whatever. We just want to boil it. So we just have these two Q's. Well, how do I, if there's a change in temperature, I use what equation? MCAT. So what's the mass? 100 grams. Specific heat of water is given, but it's 4.184 joules per gram degree Celsius. What's my change in temperature going to be? 75, and it's positive because I'm going up. It's always final minus initial, but the reality is if you're going up, it's going to be positive. If you're coming down, it's going to be negative. So it's going to be 75 degrees. Actually, I think I only have one. That's 25.0. But I said, let's say 100.0 degrees. No, that's grams. Boiling, we'll say 100.0. Okay? Just for sig figs, that's all I was worried about. Plus, somebody plug all that in. But what else, while someone's doing that, what else do we have to do? How do we do Q boil? So what's M? So what is that value? 100 grams. It's still 100 grams. Times our heat of vaporization. Now that's given to you on that sheet that we were working on yesterday, and I think it's 2264 on that sheet. And that's joules per gram. So what's this term equal? Anyone? Is that the total or is that just this one? 81,000?
31,000.
31,000. Plus this one, we can just go here, 22,6400. So 226,000 joules on this one. Look how much bigger that is. Okay? So we add those together, the total amount of energy needed to make 100 grams of water go from here to here is, add 31, 226,431. Right, it's 380. That's right. I'm off on my decimal places in my brain. 257.
780.
So how many kilojoules would that be? Okay. So how many places do we move the decimal? 3. So it's just coming here. So we say 258 kilojoules.
Is that like a lot? 258 kilojoules?
It's a good bit. Okay. Now,
How bad would it hurt?
well, just think about 100 grams of water is a pint's a pound. So 100 grams isn't that much. It's 3 ounces, a little over 3 ounces of water. So the amount of energy it's going to take to heat that up and boil it would still, though, when you think about the fire that it would take, if you put your hand on that fire, you know, the same amount of time it hurt. Okay, so here's the deal. This is joules, but heat can also be measured in calories. 4.184 joules is equal to 1 calorie. That's a food calorie. Okay? So, Okay, we're talking about calories and energy that needs to be burned, okay? So, a food calorie. A calorie is defined as the amount of energy you need to take to raise 1 gram of water 1 degree. But a food calorie is actually a kilocalorie, 1,000 calories. So a Snickers bar that is 280 calories is actually 280,000 of these calories, which would be times 4.184. That's how many joules it would be. 280,000 times 4. So it'd be almost a million joules of energy in a Snickers bar. Okay? So,
That's why you not you.
does anybody know how many calories are going to equal a pound of fat? How many calories do you have to eat to gain a pound over what you burn, or how many calories you got to burn to lose a pound?
Like 1,000 or something?
It's more than that. No? 3,500 calories is the equivalent of a pound of fat. Okay? So if you want to lose a pound, you have to burn 3,500 more calories than you take in. Okay?
It's terrible.
Yeah, it is terrible. Trust me. And as you get older, it's harder to burn. I mean, I run forever, and it just still nothing not burn like 5 calories. And so, 3,500 calories. So a nutritional calorie is actually a kilocalorie. Now the good news is when you go out and you run, then you're burning kilocalories as well. They're supposed to be on food labels. It's supposed to be a capital C for the calories, but nobody does that. It's all a little c. It's just an understood nutritional calorie, but it's supposed to be a big C for a kilocalorie. All right, so let's do another one of these. That was just on my information, by the way, just as far as the food calories and stuff. But they assume that when you eat a Snickers bar, it's just like burning it. It's just going to give off however much, if you were to, put it into fire, how much heat was given off if you burned it. That's what they assume happens in your stomach. All right, so let's do the whole thing. How much energy is needed to change a pound of ice, 454 grams of ice at negative 20 degrees Celsius to steam at 125 degrees Celsius. Take a few minutes and see what you can do, if you can figure that one out. Think about where are we starting on the graph and where are we ending and how many different Q's are you gonna have to calculate? Because you have to do it in sections. You can't do it all in one, A to B is a section, B to C is a section, C to D is a section, D to E is a section, E to F is a section. Okay, let me go through this one now. You've had a chance to look at it and think about it. Go through this one, then we're gonna do the last 3 questions on the worksheet for the rest of the period. Okay, which are 2 of them are just kind of like this type problem. Okay? So, where on this graph are we starting in this problem? Solid, it's down here. Let's just say -20 is somewhere around here. Right? Where are we ending? All the way up here. We'll just even say this one, steam, at 125. Okay? So we got to go through all the Q's. How many are there? 5. Okay? So we got to say the Q total is going to equal the Q of the ice, and the ice is going to go from -20 to 0. The ice isn't going to go all the way to the 125. You're only taking, the ice gets up to 0, then it starts to melt. The ice doesn't go all the way to 125. Then we have to melt the ice, Q melt. Then we have to take the water from 0 to what temperature? 100. Then we have to boil it. Then we have to take the now steam from what to what? 100 to 125. Okay, so those are my cues, my different steps, segments. Now, if I'm solving this and I'm sitting in your seat, I'm not going to do this next step, but just for the sake of clarity, I'm going to go ahead and just do an extra step, meaning that I'm going to say QT is going to equal then the mass of the ice times specific heat of the ice times the change in temperature of the ice, plus the mass of the ice times the heat of fusion of water, plus the mass of the water times specific heat of the water times the change in temperature of the water, plus the mass of the water times the heat of vaporization, plus mass of the steam, specific heat of the steam, change in temperature of the steam. When there's a temperature change, it's MCAP. When it's a phase change, it's mass times heat of fusion, mass times heat of vaporization. Okay? So now I just plug in. What is M going to be in every case?
454.
454. So if you're really a math nerd and you want to, you can factor out the M's, and then just have it 454 times and then have the parenthesis of everything else. But I think it's easier just to plug everything in. Now, on your sheet, they give you the specific heat of ice. What is the specific heat of ice on the front of the sheet?
Negative.
It's not negative.
2.108.
2.108?
Yes.
I meant like the temperature up there.
No. Times the change in temperatures from negative 20 to 0, so it's going to be a positive 20 degrees. Plus the 454 grams times the heat of fusion that's given again on there, which is 334 joules per gram, plus the 454 grams of water times the specific heat of water, 4.1, just 4.18 is what they give, isn't it?
4.14.
It does give the 4, okay. Times 100 degrees, plus the 454 grams, times the heat of vaporization of 2264 joules per gram, plus the 454 grams, specific heat of ice is given as what is the ice?
996.
I mean, that's steam, not ice, steam.
996.
1.996 joules per gram degrees Celsius times 25 degrees Celsius. Barely had enough room. It's a lot. Now you could just plug this all in on your calculator in one step. Just type it in just like you read it left to right, and your calculator will follow order of operations. Or you could always just do a parenthesis, this times this times this, close parenthesis, plus parenthesis, this times this, parenthesis, all the way across. But let's get each term. Because I want to compare the values, how much it takes for each term.
First one's 19140.64.
Okay, we'll just go 19,140 joules plus
151,636.
600 joules plus
190,000.
If somebody gets a different number, just let me know, because make sure we're getting this right. Okay, what did you get? I need a third person to verify which one.
Alright, with sig figs, I got 190,000.
Okay. Yeah, 3 sig figs, it's 190, right? And then this would be. All right, plus 454 times 2264.
102, 78.56. But it needs to round to.
Okay, but it's here, right? So it's 1,000,000. So let's say 1,028,000.
So do you want us to go with the 3 sig figs, or?
Well, yeah, all of these are, I mean, the 454 is a 3. So, and pretty much everything now, the specific heats are here, but this is still just 3. So 3 sig figs is pretty much gonna be your minimum number. And the last one,
22,700.
okay. So now we add all that together.
It's 141,440. I think it's 14 million.
No, it's 1.4. So we'll say 141 joules. Or 1,410 kilojoules. Do we not get that? I'm seeing some looks.
I just got something different because I did 3 sig figs on all of them.
Because I mean, here we're carrying 4 versus, and 4 and then 3.
Yeah.
Yeah.
But mine was just like
Okay.
200.
All right. So this is the total amount of energy. If I'm going to take a pound of ice from out of the freezer, freezers are around -20 degrees at your house. I take a block of ice, a 1 pound block of ice out, and I would need to boil it and make it turn into steam at 125. I'm going to have to put in 1.4 million joules. Okay. Now, of that, what percent was needed to make it boil?
The very last, no,
This one.
yeah, that.
So divide 1028, 1,028,000 divided by this number. Well, we're gonna do this one, 1410, and then times 100.
72.9%.
72, so 73% of all the energy needed to cause that conversion, 73% of it was just to make the water boil itself. Okay? Yo, that's why energy is so expensive. Because in order for us to get electricity, we have to spin a turbine. That turbine is generally spun by steam. So we have to get the water turned into steam somehow. So we can burn coal, which tends to be a little bit dirty and a lot of pollution. Okay? We can burn natural gas, which burns cleaner than coal, and it's a lot cheaper. And that's what most of the power companies are doing right now. Or we can do nuclear reaction and use this, the energy of the nucleus being split to turn the water into steam. Okay, so, but all of those, you have to have high energy outputs because it takes so much energy to boil that water. Once it's steam, it doesn't take that much to heat it up. But it takes a lot to make it boil. All right, so let's use the remaining 12 minutes or so to do, let's kind of do 8, 9, and then go back and do 7.
We have 4, 5, 6.
Oh, that's what I meant. Okay, so 5 and 6, and then go back and do 4. I just had the wrong numbers in my head. Okay, you can stop that. Have a great week.